All right, so what do we mean by average velocity versus instantaneous velocity? We covered that in the warm-up, but I want to synthesize that here. What do we mean by speed? How is speed different than velocity? And then introducing a new word, acceleration. What do we mean by average acceleration and instantaneous acceleration? Okay. So velocity is the rate of change of what function? Of position, which we can use P of t if you want, or more commonly S of t is used for position. So my average velocity is a change, I'm using the little delta symbol for change in position over change in time, right? That's exactly what we were looking at here. We found a specific average velocity over the time interval 3 to 5 seconds. So maybe if we said my position, maybe I'll use S here. If my position function is given as S of t, and I want to find the average velocity over the time interval t1 to t2, what am I going to calculate? My average velocity, scooch this down, my average velocity is going to be my position at time 2 minus my position at time 1 all over the difference in my time intervals, time 1 minus time 2. Used yellow and pink. Let's do that again. Yellow. Oh, and look, Lindsay's dyslexic. I said T1 minus T2, but I didn't write that. Beautiful. And T2. Yeah? Geometrically, that was the slope of the secant line. Right, connecting what 2 points? T1, comma, go find the position at T1. And T2, comma, go find the position at T2. Go find y when x is T2. Yeah? Secant. The instantaneous velocity, on the other hand, is the slope of my tangent line. It's still a change in position over change in time, but you're taking the limit as run goes to 0, as your change in time is going to 0. But I'm still looking at my rise, my position, over my run, change in my time, right? And we know what that is notation for. Oops, time has an E on the end of it. What is that? My velocity is the derivative of my position function. So here's your position function, S of t, and what am I going to do? I'm going to take its derivative. I think I want to write that sentence. Velocity is the derivative of what function? Of position. Geometrically, that is the slope of the tangent. And in our warm-up, you found the slope of the tangent line at a particular moment in time at t equals 2 seconds by just plugging in a 2 to my velocity function. Now, what's the difference between velocity and speed, right? Because at the beginning of the semester, I was saying just think of velocity as speed, even though it's a little bit different. Velocity has two things in it. It has a magnitude and a direction. It has a speed and it has a direction, the positive direction or the negative direction. So in the example, in the warm-up, you can see, like if I'm looking at the slope of the tangent line over here, all these slopes are negative. Velocity is negative. My particle is on its way down. Whereas here, all these slopes are positive. Positive slopes means positive velocities. My velocity is positive. That means that my particle is traveling in the positive direction, which here is up. So speed doesn't have that direction. Speed can't be negative. Speed is the absolute value of what function? Of velocity. Okay. And then something totally new is acceleration. Acceleration in math and physics means something different than in everyday life. Usually we use the word accelerate, like to accelerate, meaning to speed up, and that's not what it means in math. Acceleration is a rate of change, and it's a rate of change of the velocity function. Okay? My average acceleration is going to be a change in velocity over a change in time. Right? So if, for an example, I said, here's my velocity function, v of t, and I gave you a time interval, say t1, that's a 1, comma t2, your average acceleration is going to be your change in velocity over change in time. It's your velocity at time 2 minus your velocity at time 1 all over the difference in your time, t2 minus t1. Yeah, we're just calculating slope, and we're calculating the slope of the secant line. Right? Secant. To what curve? To my velocity curve. Right? Change in velocity over change in time. Let's say, like we did before up here, let's give the points. Right? So this is a point on what? A point on S, a point on position. Same here. So these are points on my velocity curve. T1, comma, go find the velocity at T1. And T2, comma, go find the velocity at T2. Right? Slope. Your instantaneous acceleration is going to look just like this, but what are you going to do? You're going to take a limit as your run goes to 0, your little change in time is on its way to 0, and you're looking at change in velocity over change in time. Okay, but we have an alternative notation for that. What is it? It is the derivative. So my instantaneous acceleration, I'm going to use a for the acceleration function. What is the acceleration? It is the derivative of my velocity function. Use the little prime notation, and I think I want to write that sentence. Acceleration is the derivative of what function? Of velocity. Okay, and geometrically, that's going to be the slope of the tangent line. I should have been writing slope on this one, sorry. Right there, let's write the word slope. Slope of the tangent line. To what curve? To the velocity curve. Okay, so I know I did a lot of writing, but this is actually, let's just summarize. What do we have? We have that velocity is a rate of change of position. If we're talking about average velocities, we're talking about slopes of secant lines. So we're not taking a limit, we're not taking a derivative. The instantaneous velocity, on the other hand, is the slope of the tangent line to the position curve. It is the derivative of position. Speed just is the absolute value of velocity. Make that positive. Acceleration is a rate of change of velocity. If we're talking about average accelerations, you're looking at slopes of secant lines to the velocity curve. You're just calculating that slope between 2 points. Whereas instantaneous acceleration is a rate of change of what function? Of the velocity function. It's the derivative of velocity. Excellent.